Okay, so sensitivity analysis is a way to analyze a linear programming problem after you've found a solution to determine how that solution would change if some of the numbers in the problem were to change. In real life, when you're talking about problems like this one where we have profit that needs to be maximized subject to some constraints, the numbers that are defining the profit are not something the company can really determine. They have costs of materials and labor that they have to pay, and those numbers change over time because the real world market is changing all the time. So, in order to make long term planning possible, sensitivity analysis is done to determine if you have an optimal solution, is it going to be likely that that decision will be optimal for a long future amount of time or a short future amount of time? And this involves generally a lot more than just what we're going to do in this introductory course, but this is just to get you an introduction to it. So the idea is if you have a company who's going to decide to make certain products, they have to schedule workers, they have to program their factories to make certain types of parts and then put them together. If you're constantly changing those things, you're not making products and you're losing money. So you would like to be able to decide how many of the products to make per day, per week, per month, and program that in and make sure that it's profitable. But you have to realize that the value of the dollar or any currency in the world is changing all the time, and you have to pay attention to those numbers. So what we're going to look at in this simple example is maximizing a profit. This is a problem we did earlier with a lumber company who's deciding to how many units of each type of lumber they want to process based on the profitability and the resources they have available, which are basically related to a rough saw and a plane for processing the boards. And these are tied to their employees, what employees they have trained to do those things. So there's limited numbers of hours they have for each of those resources. And each type of lumber requires a certain amount of each of those resources to process. So what we're going to look at is after we find the solution, which we've already done, ask ourselves, well, what if the profit values in the objective function were to change? How much would they have to change in order for a new decision to be made to be more optimal than the one we will decide on? So again, in this problem, we have a profit of $120 per 1,000 board feet of the finished grade lumber and $100 per 1,000 board feet of the construction grade lumber. And again, this is a simple two variable problem that we can solve graphically. We actually graph these inequalities. We actually see that one of them is redundant. It doesn't actually appear in the graphical solution. So you see our feasible region in this case is really just a triangle. And the optimal decision is to choose x to be 4 and y to be 0, which means 4,000, produce 4,000 board feet of the finished grade lumber and 0 board feet of the construction grade lumber. And you plug that into the profit function, you get a $480 profit. Now, if we go back to the problem and look at what that solution means, from thinking about what we did our simplex method, if x is 4 in the first inequality, then it actually is met as an equality. We would have 8 plus 0 equals 8. So all of those resources of the rough saw hours are being used. And the second inequality, 8 plus 0 is 8 still, but that's less than 15. So 7 plane hours that we had available are not being used for this decision. So from a practical point of view, those resources could be reallocated for other projects or possibly the number of employees could be downsized. People could be basically fired, let go to free up those resources to save money. Or the company could decide to hire more people to make more product. But the idea is this: if they have a fixed workforce of people who are going to run these machines to produce this lumber from this decision of making only finished grade lumber, what happens in 6 months if these numbers 120 and 100 in the objective function change dramatically because of costs of different materials and various other things that go on in business? If these numbers change too much, then that decision will no longer be optimal. And if you only have people who can produce finished grade lumber and it becomes no longer profitable to do so, you have to basically reinvent your entire company, and you don't want to do that. So what we're going to do in this problem is kind of go through and just ask a simple question. How does changing these numbers in the objective function lead to the same decision? And at what point do they lead to a new decision? And it's just a graphical picture. It's about lines and slopes. That's really all it is. When we get to higher variable problems, we will use Excel to help us do this. But for now, we want to understand the graphical idea of it. But that's really basically what we're going to be doing, is just allowing these numbers to be variables in some sense and to see how much they can change so that this decision that we would make is no longer any different. And the general idea is, in a business point of view, if the numbers are going to change dramatically over short periods of time, that means that your model is called sensitive, meaning you don't really want to make long-term plans based on these decisions because you're going to have to make a new decision next month or next week. But if there is a lot of room to change the numbers and still have the same optimal decision, then you can make long-term planning, and that problem would be insensitive to those numbers and how they change. So we'll just go through this and other examples just to kind of stick with two variable problems in the beginning, just to kind of see graphically what we're doing. The computations of what we're doing is very simple. It's just about lines and slopes. That's all it is. What's more important is interpreting what these numbers mean in the context of the problem. So in this case, it's a problem about making processing lumber. So we have to put it into the context.